All right, guys, you ready?
Yes.
All right. So we're on new book.
Thank you so much.
Yep. And I just printed the back side.
Printed the part, you put it in the part.
Printed the back side of that page. So you won't have a weird setup. So just insert your 11. I got 9, 10. Put that 11 in there. Then you're good.
Oh, yeah, that'll do it, yeah.
All right. And then tests. As a class, y'all did pretty good. Class average was an A.
Woo!
Believe it or not.
Yeah. I'll drive that down a little bit.
What was the class average in the first period?
Not an A. Not even.
I'll be free. Oh, yeah.
Hey, man. That's, I'm very okay with that grade right there.
Yo.
Oh, wow, I did great on the second day. It was the first day.
Yes, sir.
So Q1.
Good job. That's awesome.
So the average was a low B in first. And the average in this class was a 9.5.
Oh, my goodness.
13-point swing.
Wow.
Yeah. Was there a curve? The only curve there was is that in the classes, I graded the quiz part, that one we took that day early. I graded that 2 points apiece, which was out of 36. This was out of 68, 4 points apiece. So a total of 104. So, with the exception of JW, who got so high, I was like, I'm not giving him a 108. I just didn't do it. So, I just capped you at the capping point. And not that it matters, whatever, but I just, at some point, I was trying to help out the needy. It's like giving filet to the rich, you know, if you're trying to help out the needy.
Then just take it out of 100.
So I put it in out of 100, whatever you have. So anyway, so there was kind of, I guess, a little tiny scale in there, but not significant. All right, so jumping back to vectors, guys. So the things you probably need to have in your brain at this point are, oh, by the way, are there any questions? You didn't miss much, but if you have a question, I'll talk about it. It means extend that. So it looks like the negative's on the top and not off the
I
side.
have a question about half of those. Whether it is positive or negative, would that depend on whether it's like quadrant?
The original problem, exactly. So like you saw that in the second, so you know a cosine of the second quadrant is negative, so you use the negative. Yeah, you gotta go back to that original
So
problem.
would that be the angle before we have or after we have?
Before, because that's ultimately what you're doing, right? You're trying to find the cosine of that. So don't look at the 225, look at the 112 and go, that would have been in the second
I
quadrant.
would have gotten more points if I know.
That's all right. Anybody else got a question?
That's why I did better than I thought.
That'll do it.
I know that kind of thing.
Anybody?
Maybe back, right?
Yeah, take you back. Roll. I think our school gets like a penny for every click you have to make. You can't do anything without making 10 clicks. So annoying. Here, he's pretty south. This is really like that.
Be quiet and quiet.
Yeah, no, he is a solid guy, but like in math, really solid. Like he won that geometry club.
Really?
Yeah.
I don't like that.
Yeah. Well, they had the top 27 places.
Huh.
And that's without Jackson Kittinger, who probably has my highest average. He wasn't even there because evidently he's really good in soccer.
Oh, wow.
And the coach was like, please don't take him. And we didn't know he was any good in math because he was a homeschooler.
Oh, yeah.
So Helmers was like, I mean, he was good, but I got a lot of good. He didn't just know how good he was. So he literally gave up arguably his best math teamer, possibly. Normally you don't try to negotiate that deal, you know. But evidently he was that good in soccer. I don't know if he liked to play soccer.
I played soccer. I know one for my team.
He's really good.
Yeah.
Yeah.
I'm sorry, what is?
He's really good in math too.
That's the one. Nice to have more than that.
Oh.
All right, they have that. You want to look at him later? We can look at him later. Martina's getting bored.
Hey, Martina.
Hey, Nathan.
All right, we're going over tests, in case you're wondering. All right, so back to vectors. So vectors, we said, it was a quantity that showed or demonstrated what two things?
Magnitude and direction.
Magnitude and direction. So it's not just a directional force or a directional so-and-so like a ray is, but the length of it means something as well. Okay? We also talked about the ways you could write a vector. Component form. And component form is when you have the what? The little funny inequality looking things, we call them brackets of some sort with the comma, and you treated it kind of like a point, right? But instead of having to start at the origin and going over and up, you could start anywhere you want and go over and up, but whatever you start to wherever you finish, that's how you drew the vector. We also talked about how to find a vector from 2 points. We talked about if you have a vector, if you're given 2 points like P and Q, if I want to find the vector from P to Q, you got to first establish where am I terminating, where am I ending? I'm ending at Q. So you take the Q, X, and Y values, you subtract the P, X, and Y values from them. But if I was going vector QP, then I'd be terminating at P, and I would go that minus that, that minus that. But it just depends. You'll never see that little vector thing pointing to the left. It always points right. And it's not an arrow. It's like a line with just one little barb on it. Okay, that's how you show vector. I wish it was a little bit more pronounced than that, because most people, when they draw them, they're very pronounced. Like a physics teacher is not going to go, they're going to go to and make it a little bit easier.
So can a vector go the opposite direction, like left or down?
Sure, a vector can go, it just depends on whether or not you end up with a negative or a positive. If it's negative on the X coordinate, then head left. It's negative on the Y, head down, and then just go in whatever direction it tells you. Okay, so today what we're going to talk about is how we would get those forms if I didn't give them to you in that form, but instead I gave you the actual magnitude and the direction angle. And guys, I hope that you memorize this, but this is not a big deal. I mean, and what I mean by that is I don't want to minimize and say it's easy, because easy is relative, but very clearly, if I have a vector whose magnitude is 20, so the magnitude of the V is 20, or the length, and I know that the angle of the vector is 38, that's going to create a triangle. And the components of a vector are the X movement and then the Y movement. So I need to find out what was that movement and what was that movement. Well, guys, that's just trig. Now, if you think about the unit circle, for instance, so here's your unit circle, and I'm just going to reference 60 degrees here. All right, so what do we know about 60 degrees? We know that we went over a half up square root of 3 over 2, right? How did I get a half?
Or we have all of our 36 values.
That was the cosine of 60. That was the cosine of the angle. How did we get root 3 over 2? That was the sine of the angle. the sine of the 60, right? That's how we got those two values, cosine and sine. Well, if I want x, what do you think I'm going to do? X comes from the cosine of the angle, right? Now, I'm not just going to stop there because this is not a unit circle. This is a 20 unit. So whatever I get, multiply it by 20. Y was the sine of the angle. It's the sine of the 60. But it's not a 1 unit long circle. It is a 20 unit long. So 20. Oh, sorry. Yes, definitely. 38. Sorry. Are y'all with me? But guys, that's not even rocket science. I'm just really using trig, right? I mean, isn't cosine of an angle the x value over the r value? So to find x, don't I go r cosine theta? And if r is the magnitude, isn't that really what I'm doing here? And the same thing for sine. Isn't y over r the sine of the angle? So isn't y equal to r sine theta? And again, if r is the magnitude of the vector, I'm not trying to make this difficult. This is regular, just basic trig you learned back in geometry, and then cross multiply and solve. But I hope you don't have to draw a picture of this every day, because I'm not going to give you a picture. I'm just going to go, what are the components of this vector? You know? So if I gave you root 20 and root 38, and I said, what's the vector? You're just going to do this. Oh, so 20 cosine 38, 20 sine 38. Done. And if it was a unit circle vector, then great, simplify it all the way. But I don't know what 38 is, so I'm just going to stop right there unless I have a calculator. And if I want to put it in unit vector form, 20 cosine 38 degrees I plus 20 sine of 38 degrees j. And remember, the I and the j here don't mean imaginary I, right? That just, I tells you to go left and right with it. J tells you to go up or down with it. Y'all with me? So just make sure you understand that that's what magnitude and direction are really doing. They're just parts of a triangle which you can find components. Now, let me give you an example of components. When I was, I don't know, young, I worked at this camp in Northern California, which some of your friends have been to. I know Chandler's been a number of times. Her dad was actually a camper of mine when I did the Track 2 program. He was one of my camp kids.
Wait, is this where you
Binkley, Chandler Binkley, Track 2, do what?
That's
No, he didn't cry, he just he did really like, I'm not going any further. Just laid down in the snow, which is really hard. After you hike for 10 hours, you're pretty tired hiking straight uphill. He was like, I'm out. And that was funny to me because he's so fit. He's done freaking triathlons.
What activity involved hiking 10 hours up there?
Sorry?
Well, that activity included hiking 10 hours?
Yeah, we were hiking Mount Shasta.
Wow.
You had crampons and ice boots and stuff like that. You're going over a glacier at one point. But anyway, there was a point to this. What was my point? Oh, well, one of the summers before I did that Track 2 program, I was in charge of a group of kids for a Second Wind program. And again, you might have had some friends go to Second Wind. It's really expensive, so whatever. My kids didn't go. But anyway, when I was doing this camp, one year I got dealt these bunch of guys and girls from Houston. And they all knew each other. And normally that's not the case. But they were all in my group. And the girls were like just studs. I mean, I don't mean studs like they could bench press a car or anything, but like they were tough mentally. They were leaders. They were motivators. They never quit. They never gave up. The dudes were like, this hill is so big. And I mean, they whined about everything. Poor guys. I mean, I just, you guys can do it. And I'm like, oh my gosh, I don't think they can do it. But you guys can do it. So we got pummeled in every competition we did. which is okay. You can learn from the wins and the losses, but then the losses. But we won one thing with these skinny guys. When I say skinny, I mean they made JW look like a massive dude. They were like 5'7", $105, no strength, just anyway. We won the tug of war with 8 skinny dudes and 8, granted, athletic, but tiny girls. And you know why? Vector components. Think about this. If you are in a tug of war, do you stand like this when you hold the rope?
Nope.
Why?
You're gonna fall over.
You should just get tipped over, right? So you don't stand like this or you'll fall over too. You normally are kind of like this, right? Okay, not good enough. But if you are like this, look at my left leg. My left leg is pushing against the earth. Are you with me? So that is a vector. This is just stabilizing me, right? So I am this vector right here, if I split it into components, this vector, I'm not kidding you, we dominated it too. We wasn't even close. People are like, what is he doing? Okay, so every vector, when you, like if this is the ground, right, you're doing the tug of war, here's the rope right here, but there's the vector, right? And you're pushing against this ground. Well, this vector has, like all vectors, 2 components, an X component and a Y component, right? I want, or think about it like this way. Every action deserves, or it has an equal and opposite reaction. So what I'm trying to do is push this, I'm trying to get the rope that way, right? So if this vector, if the reaction of the vector has a component like this and a component like this, what do I want to maximize? That. I want to maximize the X component. So what do? The second they say, all right, ready, go, I told every one of my kids, hit the ground and start pulling. Literally, I want to see you in the sand. So they immediately fell over. Now, it didn't matter that my vector wasn't very big, where their vectors were huge. What mattered is I had a bigger what? X vector than they did. I just said, hit the ground. So when I hit the ground, even though my actual vector was smaller, even though my actual vector wasn't as big as their vector, right? Maybe it was smaller because we were all smaller people. My X component was larger than theirs because they're off like this, because they're idiots. Well, they don't understand physics. They're not idiots, but they didn't understand physics. We all hit the ground, maximizing our vectors, and we went to victory.
Wow.
And it wasn't even close. People are like, what on earth? Like these guys can't ride a bike up a hill. Like literally, I had guys walking their bike up tiny hills. I mean, there was no strength in them. But again, it didn't matter. We maximized the vector and we minimized the vertical component. Led to victory. Anyway,
If you're like almost lying down, it's not just like having no traction on the drag.
well, on a floor like this, that would be true. But on sand, we were in sand, yeah. So we were able to dig in, even with sand.
That's some quick thinking.
Oh yeah.
Good catching skills.
Absolutely. So this is how you're going to find your actual components. And if you're ever in charge of a tug of war, think about that. Now, it doesn't hurt having a big giant guy to anchor at the end, right? And make it, even if he's just a big blob, he's going to have to be moved, but we didn't have any of that, so we went pure physics. Okay. Also, every now and then, I'm going to ask you to double a vector, or triple a vector, or halve a vector. Now, if I had a vector that did this, for instance, say I went over 4 up 2, and that's my vector, right? So say my vector is over 4 up 2. Wouldn't it make sense that if I did half of that vector, I would be over 2 up 1? So if you really think about it, 1/2 of V, what did I really do to get half that vector? I distributed in. We call this number 1/2 if it's not a part of a vector, but it's just some other number. The same thing we do it with matrices. Do you remember what we called a number that was outside a matrix? A scalar. So a scalar number, if it's on the outside like a 6, all it is going to do is multiply in and basically take that vector 2, -5, and put 6 of them lined up in a row. Just like this half was kind of like taking half of them, but I have half a vector there, half a vector there, it halves them. Okay, so 6 of them is going to give me the vector 12, -30. -3 of them, what do you think that's going to do?
-6.
It's going to triple it and negate it. What does the negating do? Think about it. Instead of going 2 over 2 and down 5, now I'm going left 6 and up 15. It's going to send it in the opposite direction. So usually when you multiply by a scalar, multiplying by a scalar doesn't change the direction. It just extends the magnitude. With the exception is if I negate it, it reverses it 180 degrees, right? Because you're not just going in, you have opposite movements. And then again, we already talked about having the vector. So multiplying by scalars doesn't, technically, it just either reverses it or keeps it in the same direction. It just changes the length. What about adding vectors? Take a look at this. See if you can make sense of this. 2, -7. I want to add them together. Here is over 2 down 7. Okay, that's 2, -7. And I could have drawn that anywhere. I'm just drawing it starting at the origin. Now I'm going to go left 10 up 12. Left 10 up 12. Now, if I go 2, -7, left 10 up 12, where do I end up? I end up with that vector. Because I went there, then back here, so that's the resultant. Now, check it out. Take a 2, -7, add it to a -10, 12, and you add the 2 to the -10, the -7 to the 12, and you end up going left 8 up 5. Now, I don't want to draw pictures for that because it's tedious, and I have to be really exacting with my drawings, right? And I don't want to have to whip out graph paper all the time. So I like adding them like this. Or in the case of something like 2u minus 3v, twice the u, and then minus 3 the v. That would be so tedious to have to double that vector and graph it, negative triple that thing, and then add the two together. That would be so tedious. It's so easy just to distribute the 2 in. I like distributing the -3 in and then just adding. Did y'all hear that? Distribute it in, then add. Don't distribute it in and then try to multiply. And then you end up with 34, unless I'm making a careless error, -50. Because who wants to draw out a grid that's got space to draw that vector in there? Not me. Okay? So you don't really need the pictures, but what if you didn't have what this vector was? What if I just said, hey, this is v, this is u, and I said add v and u together? Well, if you don't even know what they are so that you can add their components, you have no idea, well, you can use one of 2 methods. This first one is stupid, but I remember getting taught this. The second one is you do basically what we just said. You pick v. Remember, equivalent doesn't have to start and finish in the same place, just have to have the same magnitude and direction, right? So draw the v, take the u and connect it to the end of the v, and then go from the beginning of the first one to the end of the second one, and that is your resultant vector of u plus v. So if I wanted to add these 2 vectors, I could do it that way, and literally this red vector stands for u plus v. Are you with me? The parallelogram method, this is a parallelogram method. Again, don't even have an idea of why they would do this. The parallelogram method says, watch, take your v vector, take your u vector, and then take U and put it at the end over here, and then take V and put it at the other side over here, and make a parallelogram out of it. And then you start where the two ends, where the two beginnings were, and then you end where the two ends are, and that's your resultant vector. And I'm like, it's just more work. Mind-boggling that even shows up in textbooks, but it does. But yeah, that's to me silly. Now, the only way I see maybe an advantage is if I said, hey, here's V and here's U. Like, what if I said that and said, what's U plus V? Well, then you could go, oh, if they're coming out of the same point, I could take my U. Because remember, it doesn't matter where they start, right? Take my U, put it up there. And then you could go, oh, yeah, there's my U plus V. But again, I don't know. To me, it's just easier going, why don't I just redraw that at the end of this one and then go from the beginning of the first to the end of the second. Then you don't even need this or any of that. So I'm a big fan of the head to tail. Some people call it end to end, although it's not really end to end. But it's really from the tail to the head, I think. But whatever. I've heard it called different things. But we don't do a lot with these sketching. We do a little bit at the end. You'll see a couple more examples, maybe so on the homework, but we don't do a ton with that. Okay, a couple other things, and I'm just kind of going through rules and stuff for you right now. There is something called a unit vector. A unit vector is not to be confused with unit vector form. Unit vector form is just the way we can write a vector that has an I and a J in it. And the only reason we call it unit vector form is because you use the I and the J, and it just so happens that the I is the unit vector 1, 0. J is the unit vector 0, 1. So the I, when you see it, it just means move 1 to the right. When the J, when you see it, means move 1 up. Well, if there's a 4 in front of it, like 4I, it just means move 4 that way, right? 4 units that way. Or if you see minus 3J, it means move down 3 units. Are you tracking with me? But that's why they call it unit vector form. Unit vector, not form, but vector, means you need to take a vector and shrink it down so it has a length of 1. Now, why would you want to do that? You know, it'd be like, I'm close to 6 feet tall, about 5'10". Why would you want to shrink me down to 1 foot? What use is that? There's not a lot of use, but there are some applications in physics where you want to take a vector and you want to actually find work or different things, and you want to find a unit vector normal to the ground. It's just a way you go about, it's like a little formula you use. And I haven't used it in years, and I'm not going to get into that application, but I do want to show you how to find a unit vector. So a unit vector is not a big deal. Think about it. This vector is what? 3 to the right, down 5. So this vector is clearly not 1 unit long, is it? But if I want the unit vector, I want it to be 1 unit long. How do I find the vector going in the same direction? We even did this on the unit circle, didn't we? Remember geometry? This was your relationship, wasn't it, of a 30 degree? How do we make that fit in the unit circle? Why did we have it? Why didn't we third it? Why did we fifth it? So you took the magnitude and divided everything by the magnitude? That's what the unit vector is. You take whatever the vector is and divide it by its length, which is its magnitude. So all you have to do in some situation like this is go, well, hold on. So on this thing right here, all I'm going to do is take the 3, -5. I'm going to find the magnitude of it. What is the magnitude of 3, -5? Square the 9, square the -5, square root it. So root 34. So all I have to do to find the unit vector is take 3 and divide it by root 34, and take -5 and divide it by root 34, and then put it in some form. It doesn't matter whether you go component form or unit vector form. I don't care.
rationalize them.
Of course. Yeah, always rationalize, but that's the process. So if you ever got a magnitude that was a whole number, you won't have to rationalize, but a lot of times it's going to be an irrational number. So ultimately, that's your rule for finding unit vectors. Take the vector, divide it by its magnitude, and vectors have components. So you're really taking the components and dividing them by the magnitude of the whole vector. All right? And then the last thing we're going to talk about, oh, we're way ahead of the other class. So the last thing is, how do I find a direction angle? So I'm going to give you a couple situations that are easier, and then I'm going to go to what might be trickier. So right here, let's start with B. Now the vector 4i minus 6j is like the vector 4 negative 6, right? So I'm going to draw a picture of it, but I hope that you don't have to draw a picture moving forward, that you can just know this. So if I were to draw this, I'm going to be moving 4 to the right, down 6, and this would be my vector, right? So the question is, how do you find direction angles? So how do you find that angle? You could, but what am I giving you?
A ratio.
Hold on, I'm giving you what?
4 to -65.
I'm giving you x's and y's. Sine needs a hypotenuse.
Tangent.
Tangent does not.
Cotangent.
Cotangent does not, but the problem with cotangent is I don't know anything about cotangent inverses. But I do about tangents. So again, I'm not going to write all this normally, not going to draw a picture, but let me just say, hey, if I want to find the tangent of an angle, I am typically thinking y over x. Here's the problem. How would you find it here? If I plug in the y, -6, and the x, 4, and I inverse tangent it on my calculator, what is my calculator going to give me if I'm using an angle where? First or fourth? Because that's where inverse tangent can exist. Now I know you're like, but I don't have inverse tangent, I have tangent. Absolutely. But the thing that's nice about this one is my angle is between -90 and 90, isn't it? So when I type that in my calculator, which I can do, make sure it is in degrees if you want a degree answer. So the inverse tan of -6 over 4 is -56 point, we'll call it 3 degrees. And that makes perfectly good sense because you can see it right there, can't you? Now here's the problem. What if, instead of giving you, everybody with me, stay with me here. Instead of giving you 4i minus 6j, what if I gave you -4i plus 6j? Well, now, -4 positive 6 is over here. It's not that one. Right? -4 up 6. But here's the problem. Look at the math. Y over x, 6 over -4. It's still the same math, isn't it? Aren't I still going to be typing in my calculator the inverse tan of -3/2 and -6/4? Isn't my calculator still going to spit out -56.3 because that's all it can do? It's an inverse tan. But yet I have the wrong answer. So what's the difference between what my calculator gave me and what I really want, which is this angle over here? 180. So let's think about it. How do I know whether I add 180 or not by looking at that? When would I add 180 and when would I not?
So, you know, the quadrant.
And what affects the quadrant? Look at our vector. What affects me getting out of the first or fourth? Look at the vector again.
Oh, the negative and positive.
The negative with what?
With the positive.
It doesn't matter about the y value being negative. That's up or down. What matters?
Oh, like the first dot.
The X movement, right?
Yeah.
So if you look at a problem like this and you go, wait, I'm moving left. Left immediately forces you into the second or third quadrant where inverse tan wouldn't give you an answer. So I immediately know, oh, I got to add 180. But this problem, when I look at it, I hope when you look at this right here, you go, all right, my theta is the inverse tan of -6/4, and I am not adding 180 because I am moving to the right first, +4. And if I move +4, I'm either going up or down. That keeps me in the first and fourth. Inverse tangent is fine there. Whatever I get for my answer is going to be great. But over here, if I go, hey, my angle is the inverse tan of y/x, and I type it in my calculator is still going to give me what? Hello?
A first or fourth quadrant value.
A first or fourth quadrant value, in this case, -74. And how do I know that it's going to be wrong? 0.1. How do I know that's wrong? Because I know that X value is negative, which shoved me left before I went up, right? So my vector is a second quadrant angle. Inverse tan can't give me that. But I've already recognized that instead of giving me this -1, if I just add 180 to it, just because the X was negative, that will give me the 105.9, the 105.9 that I really want. Y'all with me? But you don't always add 180. You add 180 when?
First, fourth quadrant.
When you're not in the first or fourth, right? So you know that when it's negative. That negative forces you to be second or third. A couple of different random things down here at the bottom. It says the zero vector. Guess what the zero vector is?
0.
Well, it's a vector. So it's what? It's either, it's
0, 0.
good. It's either 0, 0, or when we get to 3 dimensions, 0, 0, 0, or 0i plus 0j.
But it doesn't have no magnitude.
And it has no magnitude. And guess what else? No direction. How could it have direction? Right? I mean, where are you going? It looks more like a point. Now, if you're like, wait a minute, why am I even mentioning it if it's so useless? There's actually a use of it, and we'll talk about that later. Standard position of a vector, guess what that is? When you start at 0, 0. So standard position is when you have your initial point at 0, 0. And then just running through a couple little practice things. Find the vector in unit vector form with an initial point of that and a terminal point of that. So did I ask you for the unit vector or the vector in unit vector form? That's right. So there's no dividing by magnitude to shrink it. I just want the vector in that form. So how do I do it? If I initiate the point here and I terminate there, what is this vector? What would I do?
The X is where you subtract them, so -4 minus 5.
I go terminal. You always subtract, but you go terminal minus initial, comma, terminal minus initial. So you get terminal minus initial, -9, terminal minus initial, -9 again. Right? Find the magnitude. And,
What's unit vector form?
oh, in unit vector form. And then for unit vector form, I go -9i minus 9j. Sorry about that. So there's my vector in unit vector form. And then for magnitude, how do I find magnitude of this v? I showed the magnitude symbol to say what I'm doing. What would I do there? So I'm going to square the 7, gives me a 49. Square the -4 gives me a 16. Add them together in square root, and I get the square root of 65. How do I find the direction angle of v, which I normally go theta sub v? What do I do there for the angle?
-4/7.
No, inverse tan
So, yeah.
of -4/7. Do I add 180?
No.
Why not?
Because it's in quadrant, not 2 or 3.
Not in 2 or 3. It's in quadrant 4 because I went positive and then negative down. So my inverse tan will give me an angle there. So I go to my calculator.
Shouldn't number 1 actually be 9, 10, 11? Yeah.
What?
Yeah.
Number 1.
Oh, yes, this should be. Sorry.
Negative 9, negative.
Thanks, Carson. Put it down here again, man. I need fact checkers. So I type this in my calculator, inverse tan of -4 divided by 7, and it spits out -29.7 degrees. And I'm fine with negatives. I mean, I didn't say a certain angle had to be a positive, negative value. That's totally great. All right. What about number 3? Find the magnitude of that. Again, show your steps. Do the little absolute value thingamajigger. And what do you get?
9 plus 36, 45.
9 and 36, so root 45, which is 3 root 5. And then how do I do a direction angle of W? Inverse tan of what? -6 over -3. Do I add 180 or not?
Yes.
Why?
So it's in quadrant 3.
Because that negative on the X pushes me into quadrant 2 or 3, in this case 3, and inverse tan would not give me that angle. So I add 180 and it will give me the angle. And whatever that is, inverse tan of 2 plus a 180 spits out 243.4. Or whatever you're supposed to round to. How do I find component form if I'm given that magnitude and that direction angle? Find the component form of a vector. So that's the brackets. How do I find the x component? 4 times what? The cosine of 120. 4 times the sine of 120. And since this is a unit circle value, keep going. What is the cosine at 120? -1/2. And what's the sine? Positive root square 3 over 2. So you end up with -2 comma 2 root 3. Now this one's a little trickier. It says find the sum of vectors, V and W, if the magnitude and direction angle of V are given and the magnitude and the direction angle of W are given. Now let me show you why component forms or unit vector forms are so great. Literally, this is what you would do in a geometry class or maybe even a physics class if you didn't know vectors. You would have to do this. All right. You know, I used to actually teach this, and I would make students learn it, and they would do it, and then I would take a test on it, and then the next day I'd teach vectors, and they'd go, "You've got to be kidding me." Because this is what you have to do. You have to draw a picture of this. So you'd have kids coming in here going, all right, let's draw an accurate picture. I'm going to be 30 degrees. Here's my 30-degree angle, and my magnitude is going to be 10. So there's my vector right there. And then, since I'm going to sum these, the other one I'm going to tack on to the end of this, but now I have a 45-degree angle with a length of 10. All right, so this angle is 45, and the first angle is 30. Now what I want is the result. That. And this is the math you'd have to do. You'd have to go, well, if I want that, I'm going to need to know this little angle in here. And all I know is that this is a 10, and this is a 10. And I don't know the green side, and I don't know any of those angles, do I? all I know is that this part's a 30 right there, and that's a 45. So you would have to come in there and go, okay, if this is 30 right there, then this is a 60. And that would make this a 30, alternate interior angles. And if that's a 45, then this is a 135. So that makes that angle right there 165. So basically, I know that's 10, and this is a 165. And then you'd have to pull out law of what? Side angle side. You have to pull out law of cosines to find this magnitude. So this would be the magnitude of whatever vector we're talking about. So you pull out law of cosines. But then, once you know that, now you got to find the new direction angle. Well, the new direction angle is not the 30, it's all the way to that. So that means you're going to have to find this angle. Well, now you have side angle. So then you pull out law of sines, and you find that thing. And then add it to the 30 and get your whole thing. But here's what we can do. If I want to find the sum of these two things and find the final magnitude, all I got to do is change V to a component. 10 cosine 30, 10 sine 30. Change W, 10 cosine 45, 10 sine 45. That shouldn't be that hard. Cosine 30 squared root 3 over 2, so 5 root 3. That's not hard. Sine of 30 is a half. That's a 5. That's not hard. Cosine 45 squared root 2 over 2. Same thing over here. So if that's U and V, how do I add U and V? If that's now V and that's now W, sorry, how do I add V and W? Yeah. So all I got to do now to add V and W is add those. So 5 root 3 plus 5 root 2, comma, and add those. 5 plus 5 root 2. So there's my sum. I could type my calculator on the decimal. How do I now find the angle? Oh, sorry. How do I find the magnitude? That's the sum. So, watch, I'm done. So there's your sum. I thought maybe they were going to ask me. Isn't that a whole lot easier?
Yep.
Because think about it. The thing I described before is only going to get you the magnitude and the direction angle of it. You would then have to take the magnitude and direction and change it back into a vector. Whereas here I'm done. There's the sum of the two vectors. Done. And then the last thing, how do you find a unit vector in that direction? Now, did I say unit vector form or unit vector? So how do you shrink it? Divide each of those by the magnitude of your V. So the magnitude of my V is what? Root 29? Now, of course, you're going to want to clean that up. So negative 2 root 29 over 29. 5 root 29 over 29. With I and J or a bracket, doesn't really matter. Because I didn't specify what form. I normally keep it like it is. If it's unit vector, leave it as a unit vector form. If it's not, don't. What do you think?
Not bad at all.
Okay, guys, if you want to do well on this test, which a lot of people do, especially, well, you guys did well on this first test, but you want to keep the ball rolling, pretend there's a quiz tomorrow. And go home and study it like it's a quiz. If you do that, you're going to start being in really good shape because we don't have a whole lot of other topics to cover on vectors. I mean, you can look at it. There's dot product, there's cross product. There's some things associated with that. But our test is next Friday. Yeah, dot product. We're going to go to three vector coordinates. I mean, X, Y, Z coordinates, which is not really hard. We're going to do a little bit with cross product, trig form, equations of a plane, and review. But if you get this part down, you're going to be in great shape. All right, that's all I got. So you like the new book or you like the old subscription?
I much prefer just going at the problems.
I like having it on my phone.
Yeah.
I'm gonna get out of the big book. I can do it in school.
Well, my hope is in the next week or so, they're gonna send me a video about how to create this class where you'll have an online textbook. But if you like the way the status quo has been, like this is the first time I've used the new book, and I have the solution manual pages up there. You seen those? Right, you have to go find the problems though, a little bit. If you like it better the old way, we can stick to the old book.
What's the advantage of having to get out of the book?
No, some people said that they would rather have a textbook.
Yeah, what's the advantage of it?
I don't have an advantage. It's harder work on me because I have to go back and redo all my homework assignments. And then, like right now, if I just take pictures of the old textbook, which I've already done for next chapter, we're going back to the old way, but not because I'm trying to be a jerk. I'm trying to stay ahead. And now, but after that, if you guys are like, I like the new textbook, let's do it like we did with veterans. Okay, we'll just go full on new textbook.
Or you doing this?
Yeah.
Yeah, you didn't do homework last night?
All the.
We didn't do it.
Oh, yeah. Yeah. Oh, so look at your assignment sheet real quickly. Make sure you get this. So when you look at your assignment sheet, you're going to see, use your new textbook for these problems. But when you go to Schoology, I actually found a way to make it a little bit easier on you. When you go to Schoology, this is what you see. Yeah, it is actually, if you want to see this. Like, there's your page number. So but when you pull on them, instead of looking like it did in the past, where only the problems I assigned were there, you're going to see the whole section. So you just got to go find your problems I've assigned. So it's not a whole lot different. It's a little bit more effort, I guess, but we're talking minutes. I'm just not posting pictures of the book because you have a textbook.
Thank you. Good.
I'm sorry. See it.